Oh, there are so many yummy vegetarian options out there. You could try like lentil soup, veggie burgers, tofu stir fry. The possibilities are endless.
All right, let's jump right in. You've probably seen pictures of these massive oil refineries, just these sprawling complexes of pipes and towers. So, have you ever wondered what's stopping the whole thing from, well, exploding?
Inside every single one of those pipes, you've got fluids and gases under just immense pressure. We're talking crazy high pressures, often at blistering temperatures. The whole point of the facility is to keep all that energy contained. But what happens when things go wrong, right? A valve gets stuck, a pump fails, maybe a fire breaks out. All of a sudden, that pressure has to go somewhere, and it has to get there, like, right now.
So, as you can imagine, this isn't something you just leave to chance. The answer really is all about engineering for those what-if moments. There's a whole playbook, an engineering standard that everyone follows to make sure they've thought of everything. And that playbook is called API Standard 521. Now, don't let the name fool you. This isn't some boring, dusty document sitting on a shelf. Think of it as the master rulebook for engineers all over the world. It's literally the guide for building a plant's absolute last line of defense against disaster. Okay, so what's the ultimate goal here? It's pretty simple, actually. Every single piece of equipment, every tank, every pipe, has a pressure limit. It's like a red line that you just cannot cross. It's called the maximum allowable accumulated pressure, and the entire job of these safety systems is to make sure that no matter what happens, the pressure never ever crosses that line. So, how do they do that? How do you plan for the unpredictable? Well, engineers follow this really fascinating core principle. It's a simple but incredibly powerful idea that guides every single design choice they make, and it's called the single jeopardy rule. And here's the rule straight from the source. Basically, it says that you don't have to design a system that can handle two or more completely unrelated things going wrong at the exact same time. And that's a huge deal, right? It's a critical distinction. It allows engineers to stop worrying about these astronomically unlikely scenarios and instead focus all their energy on the stuff that could actually happen. This really breaks it down perfectly. On one hand, you have single jeopardy. This is what engineers have to plan for, one single unrelated failure at a time. So a power failure? Yep, you got to plan for that. A blocked pipe? Absolutely. Now, on the other hand, you have double jeopardy. This is what's considered too unlikely to be a design basis. For example, what are the odds of a huge fire starting at the exact same moment that a heat exchanger tube bursts somewhere else in the plant? The odds are just so vanishingly small that it's not a practical basis for design. So what this single jeopardy rule does is it gives engineers a list of credible threats that the safety system must be able to handle. We're talking about things like, okay, what happens if an outlet pipe gets totally blocked? What if the power for the whole plant just goes out, or an external fire starts up right next to a pressure vessel? Engineers have to look at every single one of these possibilities, one at a time, and figure out which one creates the absolute worst-case scenario, the highest pressure, and then they design the system to handle that. Okay, so the worst has happened. One of those single jeopardy events occurs, and the pressure starts climbing fast. The safety system kicks in, so now what? Where does all that dangerous high-pressure stuff actually go? Let's follow the journey. It all starts with a trigger, right? The overpressure event. This is that heart-stopping moment when the pressure gauge is climbing and it's getting dangerously close to that red line we talked about. This is the exact instant the whole automated safety system is designed to wake up and spring into action. And this journey has a few very clear steps. First, the pressure starts to rise. Then, bam, a safety valve automatically pops open. The best analogy really is the whistle on a tea kettle. It's that simple in principle. All that high-pressure fluid is immediately routed into a special network of pipes. Then it hits something called a knockout drum, which is super important for getting rid of any liquids. And finally, once it's just gas, it travels all the way up a tall stack to be safely burned off at the flare tip. So that first stop is the flare header. And the superhighway analogy is perfect. Imagine a huge network of roads designed to collect traffic from hundreds of different on-ramps. Those are the individual safety valves, and funnel it all safely to one single destination. That's exactly what the flare header does. All right, next up is the knockout drum, and you cannot overstate how critical this piece of equipment is. See, as all that gas is rushing through the pipes at high speed, it can drag liquid along with it. The knockout drum is basically a huge, wide-open vessel that forces everything to slow way down. The liquids get heavy and just drop out. They're knocked out of the stream. Why is this so important? because the last thing you want is what's called liquid carryover. That would literally be like shooting flaming rain out of the flare, and that is a very, very bad day.
And that brings us to the end of the line, the flare. You know, a lot of people see that flame at the top of a refinery and think it's just burning off waste. But it's not. It's an incredibly important, highly engineered safety device. Its entire purpose is to take those hazardous gases, mix them with air, and burn them completely and safely. It's turning something dangerous into something much less harmful. It really is the plant's giant, ever-vigilant safety pilot light.
Okay, so we've seen the whole journey, from the valve popping open all the way to the flare. Let's just zoom out for a second and ask the big question. Why does all this matter so much?
It matters because this entire system, from the rules in that API 521 document to the flare tip burning 100 feet in the air, it all works together as this invisible guardian. It's constantly on watch, protecting the lives of the workers inside the plant, protecting the families in the communities right next door, and protecting the environment from what would otherwise be a disaster.
So what are the big takeaways here? I think there are three. First, safety on this scale doesn't happen by accident. It is the result of exhaustive, deliberate, and brilliant design. Second, that single jeopardy rule is just a really smart, practical way to focus on credible, real-world failures instead of getting lost in the what-ifs. And finally, and this is key, the system doesn't just release dangerous pressure. It's a complete disposal system that safely collects, treats, and neutralizes the threat. At the end of the day, all of this incredible engineering is humming along silently in the background 24/7. And it kind of makes you think, doesn't it? What other invisible safety systems are all around us, protecting us every single day in ways we don't even notice?